Okay. So, generally speaking, when photon energy goes up, what happens to attenuation? So in other words, as photon energy increases, what happens to attenuation?
It decreases.
Correct. So as photon energy goes up, there's a greater chance that the photons will what? So what is it? Photon energy goes up, photons are more likely to
be transmitted.
Okay. All right. So we said as photon energy goes down, the likelihood of attenuation goes up. So what we have to do though is look specifically at what is happening in terms of attenuation. So as photon energy goes up, yes, there is a greater chance of transmission, but what you have to do though, you have to keep in mind that even though photon energy is going up, not everything is being transmitted. We still have attenuation taking place. So of the photons that are attenuated, as that photon energy goes up, fewer photons are going to be absorbed, more photons are going to be scattered. Okay. And then the opposite is true. As photon energy goes down, we know that we do get more attenuation, but specifically what's happening with attenuation? Well, with lower photon energy, we get more photoelectric and less Compton. So when it comes to wording questions and reading those questions, you really do have to pay attention to how the question is worded. If you are asked a question that says, that asks, as photon energy increases, what is most likely to happen to the X-rays? Well, what is most likely to happen is transmission. Okay. So as photon energy increases, photons are more likely to be transmitted. As photon energy goes down, photons are more likely to be attenuated. Now, if you look at a question that's worded like this, as photon energy increases, which interaction is most likely to occur? Then you are comparing photoelectric to Compton. So you really have to pay attention to how that question's worded. So as photon energy increases, which interaction is most likely to occur? Compton, right. As photon energy goes down, which interaction is more likely to occur?
Photoelectric.
Okay. If the question is not asking you about the specific interaction, then it's just talking about in general. So again, if a question says, as photon energy goes down, what is most likely to happen to the photon? So as photon energy goes down, what is most likely to happen? Attenuation, exactly. So you have to pay attention to the way that the question's worded. Okay? And something down here, I put, because textbook, mentions it. When it comes to the photoelectric effect and atomic number, the effect is proportional to the atomic number cubed. So, for example, calcium has an atomic number of 20, oxygen has an atomic number of 8. So the way they figure this out is you take 20 and divide it by 8, and then you cube it, and it equals 15.6. So what that means is, in calcium, the photoelectric effect is 15.6 more times likely to occur than in oxygen. Just wanted to show you that because you'll see that in textbooks. In terms of test taking, you may be asked a question. You won't have to figure it out, but you may be asked, what is the photoelectric effect? How is it proportional to the atomic number? What is that relationship? So you would need to know that it's proportional to Z to the 3. So atomic number in photoelectric effect is proportional to Z cubed. You will not have to figure this out though, but you're expected to recognize this. Same thing too with photon energy. It's photon energy in the photoelectric effect, it's inversely proportional. So the photoelectric effect is inversely proportional to photon energy. And this is how it's figured out, 1 over the photon energy cubed. In all honesty, for our level of understanding, this doesn't really make a lot of sense to us because it's not something that we'll use. But because it's in the current textbooks, it is information that you could potentially be tested on. So make sure that you know the photoelectric effect is proportional to photon energy by this 1 over E to the third or cubed. So you do need to recognize this as a relationship between photoelectric effect and photon energy. And you need to recognize Z cubed or Z to the third as a relationship between photoelectric effect and photon and atomic number. Okay. But you're not going to have to work those out.
E is just energy, right?
E is just the photon energy.
Okay,
Yep.
just making sure.
Yep. In KeVs, whatever that photon energy is, exactly. Yeah, you're not going to have to work that out, but you need to be able to recognize it. So what creates the image? Well, we've got transmitted X-rays, and that is our useful information. Okay? Transmitted X-rays will create the dark areas of luminance, or we can call it a low area of luminance or dark area of luminance. So when you look at the lungs, we're able to see those lungs because of the transmitted X-rays. Okay? So that's useful information. Okay? That's useful information. So dark areas of luminance here. Well, absorbed photons, they also yield useful information. And if they're absorbed, what effect is that again? Absorption occurs by what?
Photoelectric.
Photoelectric, right. And so the absorbed X-rays, they create the light or the high areas of luminance. Okay, so this is, light area of luminance, light area. If you notice, photoelectric absorption, see how that has occurred in the bone, the rib, whereas, the lungs, the dark areas, that's the transmission. So we've got those high areas of luminance, okay, of luminance. Now, the little asterisk here, keep in mind as the amount of energy absorbed in a particular structure increases, the contrast is going to increase. Okay? So this is why we want the photon to interact with the K-shell since it is most tightly bound. In order for the photoelectric effect to occur, remember that happens when the K-shell electron is knocked out of orbit. Okay? K-shell electron's knocked out of orbit. That's when that photon energy is absorbed, and that's what gives us the white colors on the image, or the light areas of luminance. Okay? And the more energy that gets absorbed, the more photoelectric interactions that occur, we get an increase in contrast in that image. We get the increase in contrast, which allows us to, it's going to help us differentiate between structures. We'll be talking more about this. But if we don't have a lot of absorption, then we're not going to have a lot of contrast. So for example, if we have too much transmission, like if this bone is transmitting too many X-rays, it's not going to show up white. The whole image will just be a dark area of luminance. So this photon absorption by the photoelectric effect is critical. That's what allows us to see the difference between these structures. It gives us contrast. This is white and this is more of a, a black color. So that's what gives us that contrast. Okay. Something else to note is this term here called differential absorption. This is something that you need to be aware of. There are tissue variations, in the structures in our human body. And that's good that we have differences between the different structures as far as their ability to absorb. If all the structures absorb the same way, then everything would end up being white. The lungs do absorb a certain number of x-rays. They do absorb a certain number. They transmit more than they absorb, but we do have a certain amount of absorption that takes place. And that's good, because if we didn't, then we wouldn't be able to see the lungs. The reason we can see the lung markings is because there is a certain amount of absorption that takes place there. Okay. On an abdomen x-ray, using the proper exposure factors, you'll be able to see the shadow of the liver and the shadow or the outline of the kidneys. And that's because a certain amount of absorption takes place in the liver and in the kidneys. Not as much as we see in bone, but it's because of different atomic number, different mass densities. But still, it's that difference in absorption between structures that allows them to be visible. So on an abdomen, we can see the bone, we can see the lumbar spine, but yet you can see the liver shadow and you can see the shadow of the kidneys. On the chest x-ray here, the heart is a soft tissue structure, but we're able to see the outline of it because it absorbs differently than bone does, and it absorbs differently than lung. So differential absorption is what allows us to see structures, and it's because they all absorb photoelectrically, but to different levels, different extent of photoelectric absorption. If everything absorbed the same, it would be white. If all the structures transmitted everything, then the image would be black. So the reason we are able to see and differentiate bone from soft tissue structures, from the air and the lungs, it's because of differential absorption. So does that make sense? Okay. Scatter is useless information. It decreases image contrast. It will make the image grayer in appearance. And we'll be talking more about this in the next PowerPoint when we do this intro to image quality. So the scattered x-rays, which is the Compton interaction, that's useless information. And we'll talk more about it. So what creates the useful information on the image? Transmission and absorption. Okay. The scattered x-rays, that's useless information. It's just areas of grayness that will decrease the contrast, so it's useless. All right. So to finish up this PowerPoint, just want to show you a couple of attenuation applications. Because we talked about attenuation in the human body, atomic number and all that, and the role it's played. So I want to focus on that a little bit more, but I also want to show you some other things. So there's something that's referred to as the half-value layer. And half-value layer means, has to do with, to put a definition with it, it's the thickness of material that reduces the beam to 1/2 of its original value. So half-value layer is the thickness of material that will reduce the beam to 1/2 of its original value. And I'm talking about the quantity. So the material that reduces the beam to 1/2 of its original quantity value. So where this half-value layer comes into play is with technique selection or exposure factor selection, and then with equipment quality control, specifically with something that's called filtration. And then attenuation also comes into play with protective apparel, specifically the photoelectric effect. So I want to show you this half-value layer as far as technique selection is concerned. As far as equipment, we'll deal with that next semester. And then I'll just mention some things to you about protective apparel, just so you can kind of get an idea. Let me show you this thing, half value layer curve or an attenuation curve. What you're looking at here is, this would be the thickness of material. So typically it's in centimeters. So it could be 1 centimeter, 2 centimeters, 3 centimeters, 4, 5. So thickness of material. And then on this axis, it's X-ray quantity or intensity. So it's a measurement of the intensity, whatever the intensity happens to be. And then this is an attenuation curve. This is an attenuation curve, okay? Which, if you think about it, hopefully will make sense. If the thickness of material increases, what happens to the number of X-ray photons that get attenuated, that get removed from the beam? As the thickness of material goes up, what happens to attenuation? And we mentioned it earlier, as thickness increases, what happens to attenuation?
Attenuation also increases.
It increases, and that's why this curve looks like this. Because when you're at a lower thickness of material, you have a high quantity of photons. But as the thickness of the material increases, the intensity or the quantity of the photons that are left in that beam will go down because they are being attenuated. So as the thickness goes up, the quantity of photons goes down. Okay, so that's an attenuation curve. So the half value layer is just simply a measurement of the thickness of material that it takes to reduce the beam to half of its original intensity. So the I stands for the intensity or the quantity of the beam. The little subscript here, the little O or 0 stands for the original. And here we're looking at half of the original. What did it take? How much material did it take to reduce the beam to half of its original thickness? So you've got a particular quantity. Let's just say, for example, to make things easy, let's say we have 400 photons. We've got 400 photons. What's half of 400?
200.
200. Okay. 200. All right. Here we've got thickness of material. And let's just pretend that, this of course would be 0 centimeters, 1 centimeter, 2 centimeters, 3 centimeters. Let's say this is 4 centimeters. 4 centimeters. So the way you look at this attenuation curve is, if you're asked, what thickness of material did it take to reduce the beam to 1/2 of its original value? You just draw an intersecting line. So if I'm at 400 here and half of 400 is 200, I draw a line over to the curve, draw it down, and if it intersects 4 centimeters, then that means it took 4 centimeters of material to reduce the beam from a quantity of 400 to 200. So these attenuation curves are used for radiation protection purposes. It's used for equipment quality control, but it's also been used for exposure factor compensation. Okay, so let me just show you a practical application so it'll make a little more sense to you. So the half value layer in human tissue, specifically when we're talking about the abdomen, basically this applies to the abdomen, is this. So about 4 centimeters of human tissue equals 1/2 value layer. So in other words, what that means is 4 centimeters of human tissue can reduce the beam's intensity to 1/2 of its original value. So it takes about 4 centimeters of human tissue to reduce the beam to 1/2 of its original value. So for example, you have a 20 centimeter abdomen, and here let's say you've got a 24 centimeter abdomen. Okay? Here we have the incoming photons. Here we have the incoming photons. Okay, the same number of photons here as we have here. Which one provides more transmission, 20 centimeters or 24?
20.
Where we have more transmission?
20 centimeters.
20 centimeters. 24 centimeters, if you happen to count the number of photons that were transmitted, it was reduced by half. So the transmission was reduced by half. So it took 4 centimeters of tissue to reduce the beam 1/2 of its original value. So we have half of what we have here. So we have less being transmitted here. Well, that means that the receptor exposure has been reduced by half, and we'll end up with a noisy image. It'll have like a grainy appearance to it. So what you can do is to restore the transmitted intensity, you can double the mass. Because if the beam was reduced to 1/2, if my intensity exiting is 1/2, if I double my mass, it will restore that intensity. So now I have the same number of photons here that I do here. So this comes from this half value layer chart. I'm not going to put this on a test and give you any examples. We may do that in the fall or in the spring. We may or may not. But as far as this test is concerned, I'm not. I just wanted to show you this is where it comes from. So this is one practical application of this thing called the half value layer. So it can be beneficial to you, like if you know you've got a good technique for a 20 centimeter abdomen, and now you've got a patient who comes in and they have a 24 centimeter abdomen, and you don't have a technique for it, you could calculate this in your mind, knowing that basically 4 centimeters is a 1/2 value layer. If the centimeters increases by 4 centimeters, then you can double your mass to keep your receptor exposure the same. You see how that works? What if you have a patient who comes in and they have a 16 centimeter abdomen? What would you do to the mass?
Double it.
You've got a technique for 20 centimeters, but they have 16 centimeter abdomen. What would you do to your mass?
Have it.
You could half it, okay? So I do expect...
Is that 4 centimeter amount, is that the same, is that just like a general number that's used for all tissue, or is it specific to like what type?
It's basically generalized just for the abdomen, and specifically when you're at around 80 kVp. We will talk a little more about this next semester. We'll get a little more specific with some KVP stuff relative to this, but I just, for right now, just for the purpose of showing you that there's a practical application to attenuation. You know, we've talked about transmission, we've talked about attenuation, and here's a practical aspect of attenuation, which actually comes from something called the half value layer, which is relative to attenuation and looking at thickness of material and how it relates, you know, to the number of photons that have been attenuated. So this is just generally speaking referring to, you know, basically referring to the abdomen. And the reason I'm saying that is because the other part of this is that it is most accurate at around 80 kVp. I don't want you to get hung up on that because we will talk more about this next semester. But for right now, you know, on a test, if you were asked, what would you need to do to your mass if the centimeters changed by 4, then you would need to know that you would either double or half your mass depending upon which way the centimeters were going. So if you increase the centimeters, you double. If you decrease the centimeters, then you half your mass. And this all comes from attenuation and this thing called the half value layer, which stemmed from the attenuation principles. So would you be able to handle that on a test if I give you something like a patient's abdomen is 20 centimeters and 10 mass is used? How much mass would you use if it's 24 centimeters?
10.
So 10 mass with 20 centimeters would be how much mass with 24 centimeters?
Oh, 20.
5.
Would be what?
20.
What'd you say, Aaron?
20.
20. Exactly. Exactly. Okay. And like I told you, we will talk about equipment QC and filtration and half value layer next semester, because this is all related to attenuation. But the photoelectric effect, want to just briefly mention this to you. There are, we'll keep it simple. With protective apparel, occupational exposure results from Compton interactions that come from the patient's body, if we're in there during a fluoro exam. So the way attenuation works in our favor is with our lead aprons. Okay? In actuality, though, we call them lead aprons, but our lead aprons are a blend of lead and tin. They're not just pure lead. It is a blend of lead and tin. And it's the reason for that is lead and tin absorb very well across the diagnostic energy range that we have. And the reason we know, if you look at an apron, the reason we know that it's not pure lead is when you look at an apron, it will say lead equivalent. They'll say lead equivalent, not just pure lead. I'm not going to ask you that on a test. I'm not going to ask you, what else is mixed in with a lead apron. I just kind of wanted you to know, it's just kind of out of interest, that it actually is not pure lead. But you do need to know that protective apparel works for us because the lead is absorbing the Compton radiation that comes from the patient. So the lead is absorbing. So since it's absorbing, what interaction is that in lead? What interaction is taking place in lead? Pardon?
Photoelectric?
Photoelectric, right. Photoelectric. So this is a practical aspect of attenuation that is used for our protection. So lead aprons will protect us from the Compton scatter, and it does that by absorbing that scatter photoelectrically. So lead aprons undergo the photoelectric absorption. And that's why it protects us. All right. So you think you have a decent handle on attenuation?